There are two mechanisms to excite mode oscillators, and therefore, in the simplest interpretation, to create particles. And there is the one possibility, which is that we have a driving force driving our oscillator, some driving force J of t. And in the case of field theory, this could be, for example, the scenario where the quantum field is the electromagnetic field with its modes, and those modes are driven by external forces, which are actually the currents and the charges. And that's why we will call that external driving force J, because currents and charges are usually denoted by J. But we will look at individual modes. Individual modes, not the entire field at once, just individual harmonic oscillators. And that's one possibility to drive a harmonic oscillator, to excite the field. Another possibility is that the constants that describe the mode might be time-dependent, such as the spring constant or the mass term in a harmonic oscillator may be time-dependent. In other words, when the frequency is time-dependent, when the natural frequency of the harmonic oscillator is time-dependent, then that too can excite the mode. In fact, you can have modes with friction term or anti-friction term, depends on the sign in front of it, so a first derivative term. If that's time-dependent, that too can drive the oscillator. And that occurs actually in cosmology, as we will see. Of course, it won't actually be friction, it will have a different origin. Well, from the expansion, of course. Now, at the moment, we are considering still case A, which is the case that's mostly considered in particle physics, where one species of particle serves as the source for another, as a driving force for another kind of particle, such as charges and currents are the driving forces for electromagnetic fields, but vice versa, electromagnetic fields also act as driving forces on the charges and the currents. And the same is true for quarks, neutrinos, and all of them. They all have a mode decomposition, and all those oscillators can be driven by other fields. Okay, so we're considering case A, external driving force. In this case, the Hamiltonian of a harmonic oscillator looks like this, the usual p squared half, and then omega squared half q squared, and we have the driving force term in Hamiltonian. If you have a driving force term J times Q, then the equations of motion will be the usual equations of motion of the harmonic oscillator, except that there is a J on the right-hand side. The Q goes away because you're calculating the commutator between P and Q, and so you get that the Dirac delta comes up at that point when you want to know the equation of motion for P dot, right? So P dot is I times P dot is the commutator between H and P. This is H, and the commutator with P picks up the term J at this point. We looked at the case where the driving force acts only for a finite amount of time. The driving force is only active from time 0 to time capital T. And before that it's switched off, and after that it's switched off. That's an important case. In particle interactions, we can usually assume that the interaction between two particles is really only very temporary. And then once they have a certain distance from each other, the particles, we might as well switch off the interaction, because they're in any case so far apart from each other. And in quantum field theory and curved space-time, you could consider the period before a black hole forms and the period after a black hole has formed, for example. And in the middle, all sorts of things happen. Harmonic oscillators get driven, etc. And in cosmology, too, you could imagine an era of space-time where you start out with Minkowski space, let's say, to keep things simple, and then a rapid acceleration of the universe happens, or just an expansion, perhaps even a shrinkage, or whatever, some non-trivial action. And then after a while, the universe goes back to just coasting, or just being even Minkowski space. In that case, too, you have the analog of having no driving, then some complicated driving, and then no driving again. And for these purposes, in these situations, it's very useful to simply skip the complicated part in the middle and focus on how things transform from the before to the afterwards. For example, how many particles were there before and how many particles will there be afterwards? So we'll exercise this here for the first time with the example of simply a driven harmonic oscillator. Now, to solve the harmonic oscillator problem, we introduced a convenient new variable, a of t, which is q plus p, q plus I times p, with suitable coefficients. And in principle, we could choose here any arbitrary alpha, any arbitrary beta. But we fine-tuned them. We chose them in a very particular way. We chose these two coefficients such that the Hamiltonian re-expressed now in terms of the A and the A dagger takes this simple form. You can always express the Hamiltonian in terms of Q, in terms of A and A dagger, even if you choose different prefactors there, because that definition is always invertible. You can always express the Q's and the P's in terms of A and A daggers. So you can always express the Hamiltonian in terms of A and A daggers, but only if you choose these particular prefactors will you have this simple form of the Hamiltonian. Okay, so that's the free Hamiltonian, and then the fourth term looks like this. That's because this here is the Q, right? So 1 over square root of 2 omega times A dagger plus A, that is Q of t. So with this definition, with this choice of new variable that encodes the information about Q and P, in its real part, in its self-adjoint part, it has the information about Q. In the anti-self-adjoint part, it has the information about P. In terms of this new variable, to solve the harmonic oscillator problem, reduces to solving these equations. Namely that IA dot is given by this, and that the commutator between A and A dagger has to be 1 for all times. For all times, because the commutator between Q and P has to be I h bar, also for all times. Now we introduce a convenient notation for the A operator at time t equals 0. Remember, we work in the Heisenberg picture, so the Q and the P are time dependent, and therefore the A will be time dependent. So we now introduce, because it's a differential equation that we will have to solve with an initial condition, we introduce a name for A, the A operator at time t equals 0. Let's call it A in for ingoing, meaning the time before t equals 0. And then later we will have an A out, which is the name for the A t equal to capital T, which is the late operator A of t. So A in and A out are simply special instances of the A of t, chosen at t equals 0 and t equal to capital T. At the moment, I mean, we have not solved it yet. Solving the problem means we actually have concretely what the A of t is as an operator on Hilbert space. So we know what the vectors in Hilbert space are and how they're being acted upon by the A. And that then gives us the true solution, which is to know what the vectors in the Hilbert space are and how the Q and the P act on them. Because once we know that, then we can calculate all expectation values, all uncertainties. Everything we want to know is an expectation value. Okay. So at the moment, we consider A in to be the name for the operator A at time t equals 0, but we don't really know yet how it is acting on a Hilbert space. We'll have to find that out. Now, the solution to this problem, to this differential equation, is actually quite easy to obtain. Notice that if this term is absent, then we have simply that I times the derivative is omega times A. That's clearly solved by an exponential ansatz, and with a constant in front, which will be the A in. But if we have this extra term here with the extra time dependence, then the solution can also be readily found, and here it is. I hope you found the time to actually check this, that when you take that function here, or equivalently, we can write it like this. I just pulled out this factor e to the power I minus I omega t because it is in common to this and in common to that. This expression is solving our equation of motion. Now, what's the form of it? Well, the form of it is this, that we have the sum of two terms, both of which are operators. The first operator is A in, and we anticipate that this is going to be a non-trivial operator in Hilbert space. But the second term is just multiplied with the identity operator. It's the identity operator, and the rest is just number valued. Okay, so what we have is the A in operator plus some function of time times the identity operator. It's a relatively simple structure. But it's our first example of what will eventually turn out to be Bogoliubov transforms. So let us now make a definition. Given that the force acts only from time equals 0 to time capital T, let us look at that interval, at that full interval, and let us give the integral from 0 to capital T a name. So that integral over the j we will call j0. j0 is by definition this expression at time t equal capital T. This expression is useful in many circumstances. If we want to know what the situation is while the force is acting, then we have to integrate only from 0 to the time t. But if we want to know what is the situation after the force has stopped acting, well, then we have to, you see, A of t, then we have to integrate all the way to a t which is larger than capital T. But as soon as little t is larger than capital T, there is no further contribution to the integral, because as we said, the force is vanishing from capital T onwards. So for all late times, for all times larger than capital T, this integral is just J0. Right? It's just integral from 0 to capital T. The remainder of the integral doesn't contribute because the J is vanishing. So that is going to be a useful number to know, a complex number. We can now write the solution in this way. A of t is A in e to the power minus I omega t at early times, before the force acted. See, it's A of t is simply this before the force acted, because the j is actually vanishing before the force acted, so there's no contribution from this. Then, while the force is acting, in the interval from 0 to capital T, well, we have to take that full expression there, see above. At late times, after the force is done with acting, we can simply write A of t is A in plus J0. A in plus J0. This thing is no longer changing as t increases over beyond capital T. And that invites a definition. You see, at early times, the time evolution of A of t is simply A in e to the power minus I omega t. At late times, it is A in plus J0 times the same factor. So, we introduced a definition that we call this operator A out. I'm using a sloppy notation already here, but I hope you can interpolate that because it's very commonly used. There should be an identity operator here, because this is an operator on Hilbert space. That is technically just a number, right? So we put an identity operator there. Actually, I had put it in here already, so it's technically it's still correct. So what we have is that if we're not interested in the middle time period while the force was acting, then we have simply that the time evolution of the A of t operator is A in times this factor for early times and A out times this factor for late times, where A out is simply A in plus J0. Now, all we've done so far is solve the differential equation. But that's not all we have to solve for. We also have to ensure that the commutation relations are valid, that they hold. And in fact, it's easy to see that if the commutation relations between A in and A in dagger are correct, oh no, this is not a good time for that. Okay. Okay, if you remember, we fine-tuned the definition of A such that the Hamiltonian took this simple form in terms of the A in A dagger, but also such that the commutation relations between X and P translated into these commutation relations for the A in A dagger. Now for A in, if we can arrange that for the A in operator the commutation relations hold, then it's easy to see that the commutation relations will also hold for the out operator at late times. In fact, here's a more general proposition. If we can arrange for the A in operator to have the correct commutation relations, then they will hold for at all times for the A of t and the A of t dagger. And the reason is simply this. So let's assume we find a Hilbert space on which the A in is acting such that its commutator with its adjoint is 1. Then the commutator between A of t and A dagger of t defined in this way, right? Defined in this way. See, A of t is a solution that has A in it. Then if we calculate now the commutator between this and its adjoint, we find that it is I as well, and it is 1 as well. The reason is that if we plug A of t, A dagger of t in here, we get that this is a non-trivial operator. That is just a multiple of the identity operator, therefore commuting with everybody. This thing is a non-trivial operator. That again is a multiple of the identity. So the only non-trivial commutator is that between A in and A in dagger. Both of them come with these prefactors there. And these two prefactors have opposite sign in the exponent, because one is A in and one is A in dagger. And that means that this big commutator becomes just this commutator times those two factors, and they just cancel each other. That is the commutator of A in, and A in dagger is 1, so it's true. So it seems that we were lucky. Our equation of motion is such that if we solve it, and we arrange that the A obeys the commutation relations at one time, it will obey the commutation relations at all time. This is not trivial. You could write down evolution equations such that the commutation relations wouldn't be preserved. It turns out that they are preserved if and only if the theory is unitary. So as long as it's generated by a Hamiltonian, this will be guaranteed. But we will see how in quantum field theory this is all quite non-trivial. So now we solved the mode equation. We solved the evolution of that harmonic oscillator, and we can now harvest the information. We have A of t after all for all times. Now the A of t translates very simply into the Q and the P of t. Remember, the Q was basically the self-adjoint part, and the P was the anti-self-adjoint part of A. So let's do this. Let's look at the early period, before the force started acting. In this case, A of t, our solution is simply this, and the Q of t is therefore 1 over square root of 2 omega, that's as it always is, and then A of t dagger plus A of t. But A of t dagger is this, A of t is that, and P of t is always I square root of omega half times A dagger of t minus A of t, which explicitly is this. Just look it up as an exercise, just look it up in the previous lectures that this is really correct. So we're harvesting that information. We know what A of t is. From that we get what Q of t is, we get what P of t is. And once we have Q of t and P of t, we can also write down what H of t is in Q and P's. Or we can write down the H of t directly in terms of the A and A dagger. And it is, of course, this. Now, in principle, the Hamiltonian has also the fourth term there, but not at early time, t smaller than 0. There's no fourth term. So we know what A of t is at early times. It's this. We plug it in here, and we get the A in dagger, A in, and two factors that cancel each other. And then that's the solution here. We find that the Hamiltonian is this. Of course, h bar is equal to 1 here. Notice that the Hamiltonian, even though we are working in the Heisenberg picture where operators are evolving in time, the Hamiltonian is not. The Hamiltonian is constant. There's simply no time dependence in it. It's a fixed operator because the A in is a fixed operator, right? It's the A of t at t equals 0. So what we see is that the Hamiltonian is strictly constant in time at early times. And we could do a very similar thing at late times. But before we do that, let's look at the Hilbert space of states. So as always, we will write our Hilbert space vectors as linear combinations of some basis vectors. Now, what basis vector should we choose for the Hilbert space? We could choose the eigenbasis of the position operator, eigenbasis of the momentum operator, eigenbasis of angular momentum operators, or things like that. But in the Heisenberg picture, we should be careful. Because in the Heisenberg picture, the position operator, for example, is dependent on time. It knows everything about the motion of whatever is going on. And so the momentum operator. So if you diagonalize the momentum operator, your diagonalization is actually time dependent. However, what we saw here is that the Hamiltonian, even in the Heisenberg picture, is time independent. So that's a good choice. Let us diagonalize the Hamiltonian. It's a self-adjoint operator after all, so it must have an eigenbasis. So we do this. Eigenbasis of the Hamiltonian at early times. The Hamiltonian at early times is given by this. We just calculated that. These are the commutation relations. And now we start with the usual construction. I assume you've seen that sort of thing before, so I hope I can go a little faster. Let's assume that there exists a vector that we denote by 0 in, and that is the vector that is annihilated by the A in operator. Okay, so the A in operator acting on this vector gives us the vector of length 0 in the Hilbert space. It's not nothing, it's the vector of length 0 in the Hilbert space. Then we can easily show that this vector is an eigenvector to our Hamiltonian. Namely, if we apply the Hamiltonian, remember it has a subscript here, t smaller 0. That's the Hamiltonian at times earlier than 0. It's constant, so I don't have to put of t in here. This Hamiltonian acting on that vector is omega a dagger a in plus 1/2 times this vector. And this a acting on that 0 in vector is annihilating it, so we are left with just the action of the 1/2 acting on that. So we have 1/2 omega on this. So what we see is that this vector 0 in is eigenvector to the Hamiltonian with eigenvalue 1/2 omega, which, well, we knew that such a vector has to exist, because for the harmonic oscillator that's just the ground state. So it's the lowest energy eigenstate of the Hamiltonian. Now let us consider the state obtained by applying the A-dagger operator on 0 in. What kind of state is that? Well, if you apply the Hamiltonian at early times on that vector that we call 1 in is just A-dagger in acting on 0 in. If you apply that here, then we get omega times A-dagger A plus 1/2. That's the Hamiltonian acting on that. We do know how the A operator acts on the 0 vector, but there is this A-dagger in the way. We can fix this by using the canonical commutation relations. And so we obtain that this is equal to omega A-dagger, and then this thing, these two get flipped around. The A-dagger is A-dagger A plus 1. That gives us this term here, plus the 1/2 carried forward, gives us that term. And so overall we get a 1/2 from this, a 1 from there, and this term annihilates with the 0 in vector. So we get omega times 3/2 A-dagger. So what we get is that the Hamiltonian acting on that vector gives us the same vector again multiplied with 3/2 omega. So this is an eigenstate of the Hamiltonian as well with eigenvectors 3/2 omega. Okay. Is this vector normalized? I hope you've all done that kind of calculation. Has anybody not done this Fock space calculation before? If so, I can point you to literature if you want. Everybody seen that before? Good. Okay. Right. So then the proposition is that the set of vectors that you obtain by repeatedly doing this, namely applying A-dagger operators on the 0 in vector, normalizing it in this way, gives you an actual orthonormal set of vectors which diagonalize the Hamiltonian. It's a nice exercise if you haven't done it yet to verify that. So these vectors n in are the eigenvectors of the Hamiltonian, the early Hamiltonian, with eigenvalues En, where the eigenvalue spectrum is h bar omega n plus 1/2. And that in fact is the complete eigenbasis of the Hamiltonian. Okay, so the logic was the Hamiltonian is constant at early times. It has one eigenbasis for all early times. That eigenbasis is called n in. And therefore we can now expand every arbitrary vector in the Hilbert space in terms of this so-called in basis, the basis of in vectors. For example, the state of our quantum system could be 5n, which is the 5th excited state of the harmonic oscillator at early times. And remember that the system stays in that state, 5n, and that's a very important point, it will stay in that state. If you at early times prepared the state to be the 5n state, the 5th excited state of the harmonic oscillator, it will stay in that state, even after the force starts acting. The force can do whatever it wants, the system will stay in that state. That Hilbert space vector will keep describing the state that the system is in. The reason is that this is the Heisenberg picture. Okay? So if, for example, we start out with the harmonic oscillator in its ground state, so the state of the system is 0 in, then there could be, a huge force shaking on our harmonic oscillator. The state stays that, just by definition, it's the Heisenberg picture. But we have to get used to this. Okay. What's important is that, of course, the harmonic oscillator can get excited. But how do we see that then? If the state stays the same, is always the same Hilbert space vector, how do we know that it's excited later on, after the force has acted? Well, the point is that if, for example, we prepare the system in its 5th excited state early on, then the force acts, well then, this particular vector in the Hilbert space will generally no longer be the 5th excited state of the harmonic oscillator. It simply will lose its interpretation as the 5th excited state. And that's because the Hamiltonian itself changed. So it takes a little getting used to this change of picture to the Heisenberg picture, but that's how it goes. So now at late times, after the force ceased to act, well, first of all, when the force acts, h of t starts to be time dependent. And when the force then finished acting at t larger than capital T, then the Hamiltonian becomes this Hamiltonian, where the j term is again absent, because by assumption, j is 0 for all t larger than capital T. And we know what a of t is at late times. The a of t at late times is simply a out times e to the power of minus I omega t. So at late times, the Hamiltonian is omega, and then this becomes a out times e to the power I omega t, and that becomes a out e to the power of minus I omega t, and the 1/2 is carried forward. Where remember the a out is the same as the a in, but plus j naught. A out is a in plus j naught. Okay, so what we have is that the Hamiltonian is omega times a dagger out a out plus 1/2. This looks just the same. It's just identical to the Hamiltonian at early times, except that now these are the out operators. And notice that the out operators, as we verified earlier, obey the same commutation relations as did the in operators. Therefore, we can go through the same motions as before. And we can say, let's find a Hilbert space representation for them. Let's identify vectors in Hilbert space and identify how those guys act on them, as we did before, but now for the out operators rather than for the in operators. So we say, is there an eigenvector, is there a vector that is annihilated by a out? Since this is a harmonic oscillator, Hamiltonian, with the same form as before, and the commutation is the same as before, yeah, we know that it's going to be true. There's going to be a vector in a Hilbert space that obeys that. And then we build on that. We do the so-called Fock construction by applying now a dagger out operators on the zero out vector. And just everything the same as what we did for the in vectors. Now, let's compare the early times to the late times. We will consider 4 aspects of the before and the after. One is the motion. What about the expectation values of Q and P? How do we see that a force will make the harmonic oscillator actually shake and oscillate? That's important because that's going to be the field amplitudes later on, right? The Q in the harmonic oscillator is elongation, but in quantum field theory, this is going to be the field amplitude. Then let's look at the phenomenon of resonance. What does resonant driving do in the Heisenberg picture with our solution just now? How do we see resonance occurring? What about the energy flow in this? And what about the energy eigenstates? This will touch on the topic of particle creation then. Okay, so for this purpose, we start out assuming that the harmonic oscillator is initially prepared in its ground state. So the harmonic oscillator is prepared in the state 0 in. And therefore will always stay in that state, even when the force acts. Then, the first thing we wanted to consider, among those 4 points, A, B, C, D, was the motion. Okay, so here's the elongation, the Q bar, the expectation value of Q. Remember, the operator is time dependent in the Heisenberg picture, and this is the solution explicitly. And we can plug in what the A of t and A dagger of t is at early times. At early times, the A of t is simply A in times e to the power minus I omega t. And the A dagger is just the dagger of that. We plug it all in here, and we see that this vector applied to that gives us just a 0. And the A dagger operator acting on that also gives us a 0, because A on 0 equals 0 has as its Hermitian conjugate equation the equation that A dagger acting on the left on A in is vanishing. Another way to see the same thing is to say that A dagger acting on the 0 in vector will create the 1 in vector, which is orthogonal to the 0 in vector. Okay, so in the ground state of the harmonic oscillator, the expectation value of the elongation or position is 0. Of course, we expected that, because at early times, that's just what the ground state of the harmonic oscillator looks like. It's a Gaussian, and the expectation value is 0, because the Gaussian is centered around 0. Now, at late times, let's do the same exercise. Calculate again what is the position expectation value as a function of time. Again, the state has not changed, same gamma, same Hilbert space vector. The q hat of t, though, has evolved. And q hat of t is always this linear combination of A and A dagger. And our gamma is 0 in, right? Because that state never changes. At late times, the A of t is given by A out times e to the power minus I omega t. Here's the Hermitian conjugate. And now we have that the A out is acting on 0 in. We have no reason to believe that this is 0. Why would it be? This is annihilated by the vector A in, but not by the operator A in, but not necessarily by A out. So in order to further evaluate what that is, we remember now that A out is actually A in plus J naught. All right, so we plug that in, A in plus J naught, A in dagger plus J naught star. And then the A in annihilates that vector, the A in dagger annihilates that vector, and we are left with this combination of J naught and J naught star. And what we find is this. We find that the position expectation value of the harmonic oscillator as a function of time after the force has acted is given by this expression here. And that is not 0. In general, this is not vanishing. Instead, it's something that's oscillating with t. Right? It's a function of t, and as a function of t, that expectation value is in this sign here. So the whole thing is going to be oscillatory because there is the sign of t. And that's what we should have expected. We had a harmonic oscillator in its ground state. A force was shaking it. The force is done now, but the oscillator keeps shaking. And similarly, you could calculate what the expectation value of the momentum operator would be, or you could also calculate the expectation value of q squared, expectation value of p squared, and once you have that, you can calculate the uncertainties too, for example. Now, the next phenomenon we want to look at in comparison of early times to late times is resonance. The amplitude, the first observation is that the amplitude of these oscillations at late times, this amplitude is determined by J0. That's what comes from that equation here. Right? At late times, the amplitude of these oscillations is given by the amplitude of J0. It's clear, it's just this integral here. And when is that amplitude strong? When is that amplitude large? Well, it is large when the integral over this function times that function is large. But you see, this is a Fourier sine transform. You're integrating here sine of t prime with j of t prime over a finite interval. So you're essentially calculating the Fourier sine coefficient of J for that interval here. So if J has a strong Fourier component with this frequency, then this integral can be large. If it doesn't have that Fourier component on that interval, that Fourier series component, then it will be 0. So that's the phenomenon of resonance. The amount of frequency omega that is contained in J of t prime is the amount of excitation that the harmonic oscillator will experience. See, if you look at it more closely here, I mean, this expression stems from that expression, and let's look at J naught, right? If J naught has a large modulus, that's when we have resonance. That's when we have that the Q of t, the expectation value of Q of t is varying a lot. So J naught is, again, this integral here, that integral here, and it is large when the inner product between this function and that function is large. So it's a Fourier series transform because we're integrating over only a finite interval rather than the entire real line. So this integral is picking out the component of the natural frequency of the harmonic oscillator that is contained in J of t. How much of the omega frequency is in J of t? This is determining whether the harmonic oscillator is oscillating after the driving force is done. For example, you could design a driving force in such a way such that this integral is completely off-resonant, entirely off-resonant, so that the integral is 0. In this case, the driving force would drive the harmonic oscillator, but then when the driving force is done, the harmonic oscillator would be back in the ground state. Can be done. Okay, now let's compare the energy before and after the driving. For early times, the Hamiltonian's expectation value is given by 0 in, and then the early Hamiltonian, the A in operator is acting on the 0 in, that's just vanishing, so we just have the 1/2. That's 1/2 h bar omega, the ground state energy of the harmonic oscillator at early times. Now, at late times, the expectation value of the Hamiltonian is again given by expectation value for the same state gamma, which is still 0 in because of the Heisenberg picture, but the h of t consists of the a of t's, and the a of t at late time are really the a out. So the Hamiltonian at late times is this, and the thing is that we have again a out operators acting on 0 in vectors, so we should remember in order to evaluate that the a out operator is the a in operator plus j0. That's what I'm doing here. Going from here to there, I just replace the a out by the a in plus j0. Then the a in is annihilating that. The a in dagger is annihilating to the left-hand side. And overall, we get now this value for the vacuum energy. For the energy of the harmonic oscillator after the driving is over. And what we see is that the energy has been elevated. Before the driving, this was the amount of energy that it had, and now after the driving, it acquired a J naught modulus squared. So again, it's a matter of resonance. The larger the J naught is, the more energy will the harmonic oscillator have absorbed. This is very much the case in electrodynamics, for example, where if you want to use charges and currents to excite photonic modes of the electromagnetic field, then it's most efficient if you drive the charges and currents at the frequency of the electromagnetic waves that you want to excite. Just matching the J of the charges and currents to the frequency of the mode that you'd like to excite. Now, what are implications? First of all, we notice that at late times, the energy is elevated, right? And what that means is that clearly the state of the system, gamma, which has been zero in all along, because of the Heisenberg picture, this vector in the Hilbert space can no longer be at late times, it can no longer be the eigenstate of the Hamiltonian with lowest energy, right? Because it has a higher energy. So clearly the Hamiltonian has changed in Hilbert space through the action of the force in such a way that this old vector there is no longer the ground state. Indeed, what is the ground state vector now? Well, the ground state vector, zero out, of the late time Hamiltonian, the ground state vector is zero out. And its energy is still 1/2 h bar omega. It's still just a free harmonic oscillator. At late times, no force. The Hamiltonian is still just a Hamiltonian of a free harmonic oscillator. But you see, it has rotated in Hilbert space. The vector that used to be its ground state vector, zero in, is no longer the ground state vector because now zero out is the ground state vector. Later on, we will calculate zero out in terms of zero in and vice versa. Now, let us relate the A out and A in vectors. Let us reconsider how they are connected. We know that the action of the A out vector on the state of the system, the A in, can be written as A in plus J naught, zero in. In other words, A out acting on the zero in vector is given by J naught acting on the zero in vector, or gamma. That's a very important equation, right? You see, A out acting on the zero in vector, gamma, is equal to J naught acting on the zero in vector A in, because this one annihilates that vector, right? So we just have left that A out on gamma is J naught on gamma. So the original, so this equation, for example, is saying that zero out is eigenvector to eigenvalue 0 of A out. This equation we can now rephrase as saying that the vector gamma is, which is not the zero out but the zero in is also eigenvector to A out, but not with eigenvalue 0 but with eigenvalue J naught. So what we have seen here is that the vector in the Hilbert space that used to be the ground state of the harmonic oscillator is no longer the ground state of the harmonic oscillator. But what kind of state is it at late times? Well, at late times, we found out something very important about that vector. The vector zero in is eigenvector to the A out operator with an eigenvalue that's not 0. Now, a vector in Hilbert space, which is an eigenstate of a lowering operator A, in our case here, namely of A out, is what is called a coherent state. Okay, so that's the general definition. If you have an eigenvector to an A operator with an arbitrary eigenvalue, then that vector, this eigenvector of an annihilation operator, will be called a coherent state. Coherent states have a particular property that makes that has important consequences for physics. Coherent states saturate the uncertainty relation. So the general claim is that if you have an eigenvector to an arbitrary eigenvalue of an annihilation operator, it will saturate the uncertainty relation. In the sense that if you calculate the position uncertainty, multiply it with the momentum uncertainty in the coherent state, then you're going to get h bar half. This means that these states, the coherent states, are the closest thing to being a classical state in the specific sense that the uncertainties in Q and P, the product of the uncertainties, is as small as it gets. The quantum fluctuations are as small as they could possibly be. So for example, you might have that the Q see, there's never a state psi. There is no state psi which would be an eigenvector to Q and an eigenvector to P, because Q and P don't commute. But coherent states get you as close as possible to a state that would be an eigenvector to Q and an eigenvector to P, with the eigenvalues being the expectation values. So they don't actually obey that, but they get as close as possible to it. And in practice, this can be very close. Now, closeness or not has to be made well defined by comparing with something. And what you compare here with is the expectation value. Often in experiments, you have expectation values of the Q's and the P's that are very much larger than the uncertainties in the Q's and the P's. In this case, the behavior is almost classical, because the quantum fluctuations are small as compared to the expectation values. And coherent states are the best thing to get to that, because you make the quantum fluctuations as small as possible. So here's a little exercise, if you haven't done it before. Show that if alpha is an eigenvector to an annihilation operator with eigenvalue alpha, where alpha is some complex number, and with the definitions that Q is this and P is that, as we carefully fine-tuned earlier, these are the definitions. If you define A and A dagger this way, remember that these equations don't define Q and P. These two equations define A and A dagger, right? So Q and P are the physical observables. They are just out there in nature. But the A and A dagger we get to define, and we define the A and A dagger in such a way that they are the appropriate linear combinations for these equations to hold. Well then, and that's the exercise, show that the expectation value of Q is given by that expression, the expectation value of P given by this expression, basically the real part and the imaginary part of the eigenvalue. Right? So a coherent state has a complex eigenvalue, and the real part gives you the expectation value of Q, the imaginary part gives you the expectation value of P, up to those prefactors here, and show that when you calculate the uncertainty in Q, uncertainty in P, their product is always 1/2. All you need to know to prove this is this and that. And of course the definition of how you calculate the variance, how do you calculate the standard deviation, right? It's the expectation value of the delta Q squared is the expectation value of Q squared minus the expectation value of Q squared. Okay, now two important remarks about coherent states. It is often said that the A operator is annihilating particles and the A dagger operator is creating a particle. They're also called the ladder operators for that reason. And we can see how that makes sense when you talk about Fock states, because you apply the A dagger operator on the nth eigenstate, you get something that's proportional to the n plus first eigenstate. That should not confuse us, however, into believing that every time you apply an A dagger operator onto a state, you're actually increasing the excitation by 1. Or that when you apply the A onto a state, it will actually decrease the excitation by 1. or that actually the particle number will go up if you apply a dagger, or that the particle number will go down when you apply A to it. That's just not the case. It's the case for Fock states, but not otherwise. For example, we have counterexamples right here. Coherent states. A coherent state has a finite expectation value for the number operator, basically the energy. But what happens if you apply A on a coherent state? Well, you get the coherent state again, and therefore the same number of excitation. Right? If this is about the field mode, if you have an electromagnetic field, for example, in a coherent state, and you apply an A operator on it, you get the same state again. Not with a photon less, but the same state again. Okay, so that's just to say that we have to be careful calling the A and A dagger operators creation and annihilation operators. And the second remark is that when we work with coherent states, and we say, okay, such a state in Hilbert space is eigenstate to the annihilation operator, or A operator, with some complex eigenvalue. And we say, okay, these are the definitions of the A and A dagger operators. Then, by the way, in terms of quantum electrodynamics, these things would also be called quadratures. But never mind the definition. When we do this, then the rest follows, right? But remember that we fine-tuned those definitions. We fine-tuned those definitions when we really didn't have to. It was our choice to choose these coefficients in front of the A and A daggers in such a way that the XP commutation relations gave us the correct A and A dagger, the convenient A and A dagger commutation relations of A dagger commutator is 1. And that fixed one variable. And the other variable was fixed by requiring that the Hamiltonian takes a very simple form. That the A dagger squared terms go away, the A squared terms go away. Now, we certainly want to keep the first requirement, namely that the XP commutation relations, the QP commutation relations translate into very simple A dagger commutation relations with a 1 there. We want to keep that. But we still have a lot of freedom. In particular, we could choose our definitions differently, namely such that the A and A dagger operators that we obtain are making not our Hamiltonian as simple as possible, but maybe that they make somebody else's Hamiltonian with a different frequency as simple as possible. You see, this is adjusted. There's a particular omega in there. For every Hamiltonian, you have to do that separately. For every harmonic oscillator, you have to choose your constant separately, such that the Hamiltonian becomes as simple as possible, that it becomes diagonal in the Fock basis. And what happens if you choose your definition here to have omega primes? It's not the omega of your harmonic oscillator. It's the omega of some other frequency harmonic oscillator. Well, you can still go through the calculation, and you find that they're going to be minimum uncertainty states. They're going to be at the boundary of the uncertainty principle. But then in this case, they are not called coherent states. In this case, they're called squeeze states. Basically, one man's squeeze state is another man's coherent state. It depends what harmonic oscillator you have in mind, which harmonic oscillator you have in mind. And you can always choose states other than the coherent states for a given harmonic oscillator. And what it means is that in the uncertainty principle, you're moving around the boundary of the uncertainty principle. That's what this extra parameter gives you when you change the frequency there. All right. And of course, in practice, it can be very useful to make delta Q, for example, very small, if that's what you need with high accuracy at the expense of making the delta P larger. And so you go into the squeeze states then, or the other way around. You can make the delta P small and the delta Q larger. So in practice, squeeze states come up quite a bit, for example, in quantum optics. Okay, but what we found is that if you take a harmonic oscillator in its ground state, which by the way is a coherent state, because it's eigenvalue 0 to the A operator, right? If you take a harmonic oscillator in its ground state, and then you drive it with a harmonic oscillator for a while, well then, the harmonic oscillator is always going to end up in a coherent state. What might be the significance of this? Now, consider the example of classical currents and charges driving the mode oscillators of the electromagnetic field. In the case of the electromagnetic field, the Q's and the P's, or the phi and the pi of the electromagnetic field are essentially the E and the B fields. And what we are seeing here from our results just now is that if you excite the electromagnetic field through classical driving forces, namely classical charges and currents, then if the electromagnetic field was in the vacuum before, then afterwards it's going to be in a coherent state. So the state of the field of photons is going to be in a coherent state. All of the modes are going to be in coherent states. Some modes are going to be more excited, some are going to be less excited, but they're all going to be in coherent states. And how much they're excited depends on the frequency distribution of the currents and the charges. It's the phenomenon of resonance. Okay, so if you... now, what does that mean for this for that kind of electromagnetic field? Let's say you take an electron and you expose it to such an electromagnetic field. What does that mean? Well, it means that this electromagnetic field will that the electron will experience this electromagnetic field as if it were almost classical. That's because, in general, the electric fields and the magnetic fields expectation values are going to come out way larger than the fluctuations in the electric and the magnetic field. Because it's in a coherent state, the electromagnetic field. The uncertainty in E and the uncertainty in B, the product at least, is going to be as small as it can be. So if you do that macroscopically, chances are that the quantum fluctuations of the electromagnetic field are going to be very small as compared to the expectation values of it. And that means that an electron moving in such an electromagnetic field will basically experience it as if it was a classical background field. Which means that you can write down the Schrödinger equation, the usual Schrödinger equation for the electron, minus IH bar d by dt psi equal to p squared over 2m psi, and then plus the electromagnetic field, let's say electromagnetic potential, V of x times psi of t. The Schrödinger equation simply has the electromagnetic field as a classical field entered into it. So this is an important point, because we think generally of quantum field theory as being something more sophisticated than Schrödinger quantum mechanics. But remember that historically, Maxwell's equations came way before the Schrödinger equation. And the electromagnetic field is definitely a field. There is no first quantization description of photons. They only exist in second quantization, massless fields. So in a sense, the quantum field theory of electromagnetism came before the Schrödinger equation. But why was it not recognized that electromagnetic theory is a quantum field theory, is second quantized? Well, the reason is that generally, when you create light or electromagnetic waves, they come out in coherent states, because the external driving will create a coherent state. So the electromagnetic field does its best to hide the fact that it's quantum. It's generally coming out in low quantum fluctuation states. This can be made more accurate. Now, I don't know how much background you have in quantum mechanics, in quantum information, but let me just close with a few comments to make that a bit more precise. Consider two quantum systems, system A and system B. You can view them as evolving independently, so there's just system A evolving, there's system B evolving, and they might be evolving unitarily. If they're not interacting, then they will be just independently evolving. You can also view the total system of A and B together as one quantum system, which is then unitarily evolving. You always have this option when you have two systems to consider them as either two systems or bunch them together and say there's one big Hilbert space, one big Hamiltonian, and the whole thing evolves unitarily. To make it more concrete, for example, you could have one system which is a hydrogen atom, it's the electron of the hydrogen atom, it's the Schrödinger equation, and the other system might be the system of the electromagnetic quantum field, with all of its many mode oscillators and all that stuff, right? So we have two quantum systems now. The Schrödinger equation for a hydrogen atom, and we have the quantum electrodynamics of the electromagnetic field. Two quantum systems. In principle, we could, as long as they don't interact, we could just say, well, they evolve independently. But we could bunch them together and then write down a Hamiltonian for just the hydrogen atom in first quantization and a Hamiltonian for the quantum field. And an interaction Hamiltonian between the two. Now, coming back to the abstract picture, when you have an arbitrary quantum system, as long as it's not being measured, it is thought to evolve unitarily. And then when you measure it, you may have a wave function collapse and so on. But the measurement process itself is really just the interaction with another system. So we can always view this process that just happened as the following happening. Our system and a measurement apparatus system are evolving freely until the measurement takes place, which is when the two systems interact. And then after the measurement has taken place, the two systems fly apart again. So overall, we have two systems, A and B, and they start out non-interacting, then they interact for a while, then they're non-interacting again. The overall process can be viewed in two ways. Either we say we have one system, system A, it's being measured. It's evolving unitarily, the measurement makes the wave function collapse, and it's evolving unitarily again. But if it started out in a pure state, because of the measurement process, it ended up in a mixed state. Because the outcome of the measurement has a certain distribution, and so they have a certain distribution of pure states after that measurement. That's one way of looking at that. The other way of looking at this is to say, okay, I have those two quantum systems, and they're simply interacting with each other. The total system, consisting of our system plus the measurement apparatus system, that total system is simply evolving unitarily. And the measurement process is just an interaction. If we do that, then we can calculate the collapse of the wave function. See, we have a total system consisting of our system plus the measurement apparatus system, and they start out both in a pure state. Then they evolve, they start interacting, which means that their state becomes entangled. Then they move apart again. Now they're in an entangled state. If you trace over the measurement apparatus, now our system is in a mixed state. It's the mixed states after the measurement. So these are two equivalent ways of doing these things. And now, in view of that picture, we can reconsider something that you were told in your first course on quantum mechanics that you should not have believed. In the first course on Schrödinger quantum mechanics, you're being told that you can write down the Schrödinger equation with the potential in there, the electromagnetic potential in there, V of x, as just a function, right? But you could have asked your prof, really? I'm having two systems here. There is the system of the electron that's moving, and there's the system of the electromagnetic field. And those two systems are interacting with each other. Chances are they get entangled with each other. Therefore, they measure each other. Therefore, the wave functions should collapse. when an electron is interacting with an electromagnetic field, it is certainly interacting with a system strongly. Therefore, the electron ought to decohere. Should its wave function not collapse? Let's say an electron is traveling happily alone, and then it comes into an area of strong magnetic field, and it is forced to go in circles. That's a strong interaction between the electron and the electromagnetic field. Why is the electron not being decohered? Why is its wave function not collapsing? How come that we are allowed to describe what's happening as a classical magnetic field entered in the Hamiltonian? Something like P, the momentum of the electron, multiplied with the B field. Now, P vector times B vector. That's what we put into the Schrödinger equation. And why can we do that? Why can we put the B vector field as a classical field in there? It's a strong interaction between two quantum systems. Shouldn't they measure each other? Shouldn't they decohere each other? Shouldn't they collapse each other's wave functions? Now, what we study today explains why you get away with it in Schrödinger quantum mechanics. And the reason is that we're implicitly assuming that the electromagnetic field that we're dealing with is in a state that's almost classical. It's in a state where the quantum fluctuations are small compared to the expectation values. And now I'd like to show you why that implies that the evolution of the electron is almost unitary. Okay, so the point is that not every interaction constitutes a measurement. Consider the quantum systems of the electron and the electromagnetic field. If we want to do it cleanly, then we have to say that this is a total quantum system consisting of the electron and the electromagnetic field. And there is the total Hamiltonian, which is the Hamiltonian of the electromagnetic field acting on the Hilbert space of the electromagnetic field, tensor the identity on the Hilbert space of our electron, plus the operator that acts as the identity on the Hilbert space of the electromagnetic field, tensor the free Hamiltonian of the electron, plus the interaction Hamiltonian between the electron and the electromagnetic field. Two quantum systems, their free Hamiltonians and their interaction Hamiltonian. The interaction Hamiltonian could be, for example, P tensor B. There should also be vector symbols there. All right, so that's the Hamiltonian, and that's the interaction Hamiltonian. And now assume that the initial state of the total system is an unentangled state. So we have our free electron moving along happily and independently. And here we have the state of the electromagnetic field, which might be a vacuum almost everywhere, but maybe there's a region where we have a strong magnetic field, for example. But then, in general, the time evolution operator takes this form. Time evolution operator is e to the power minus it times the total Hamiltonian. The whole shebang, right? There's two free Hamiltonians plus the interaction Hamiltonian. Needs to be exponentiated here. Then in the Schrödinger picture, this looks like that. Here is the initial state of the free, happily alone moving electron, and here is the quantum state of the electromagnetic field. And they are not entangled, clearly, because it's just a tensor product between the two, not entangled. But now this monster here is acting on that non-entangled state. And, well, if it was only that operator that was acting on our non-entangled state, then it would remain non-entangled, because it acts as the identity here on one of the two tensor factors, and then it can rotate only the other, so it's basically only moving this one around without moving that one around, right? And that one too is not entangling. That operator is not entangling either for the same reason. And you can do one after the other or even simultaneously, it's not going to be entangling, but this one is entangling, right? Because that is going to non-trivially affect this one and at the same time also that one. And we get all sorts of linear combinations of them because it's exponentiated, etc. It's going to be quickly entangled in principle. Right? So if you have an electron moving through an electromagnetic field, the state of the electron is quickly going to become entangled with the state of the electromagnetic field. That's what we should canonically expect. Oh, what was that? Okay. So again, the reason is that this operator is of that form, innocent. That operator is of that form, again, not entangling. But this operator here is of the form x tensor y, where both are non-trivial operators. That thing is entangling. So what that means is that after a little while, the electron and the electromagnetic field are going to be entangled. So we have this case of a composite system, a bipartite system. If we now trace over the electromagnetic field, then the quantum mechanics of the electron alone becomes the quantum mechanics of an electron that decoheres. It starts out in pure state, but because it got entangled with the electromagnetic field, when we trace over the electromagnetic field, the electron now will be in a mixed state. So if we take this trace, this partial trace here, so the state of the electron over time is given by the total state of the bipartite system over time, which is simply the ket bra of that vector here, right? It's the ket and bra of psi of t, psi of t. If we take the partial trace over the Hilbert space of only the electromagnetic field, we get the density matrix of just the electron. And that thing is going to be non-pure. It's going to be mixed as soon as the two systems become entangled. However, and this is where what we just found out about these harmonic oscillators comes in. However, if it is a good approximation, whenever it is a good approximation, that the B operator, the B field operator acting on the electromagnetic field is almost giving you back the same electromagnetic field vector with some number in front of it. So if it were an eigenvector of the field, then that would be perfect. Right? So if the electromagnetic field was in an eigenstate of the momentum operator, then this would not be an entangling interaction. And the reason is that if B hat acting on the electromagnetic field here, oh, I should have flipped it too. If the B hat acting on the electromagnetic field gives you just an eigenvalue times the electromagnetic field vector, then you could replace that operator here by the eigenvalue times the identity, right? So if this thing was acting here on an eigenvector, then you could replace the operator by an eigenvalue times the identity operator, but then that would make that term of the same form as this one, non-entangling. But if it's not entangling, then after tracing over the electromagnetic field, the state of the electron alone would remain pure. The evolution of the electron alone would be pure. Now, we don't have that ever, because an eigenstate to the magnetic field operator would have a delta B equals 0. By the uncertainty principle, it would mean that delta E is infinite. So we can't have that, but we can get pretty close. It turns out that the coherent states that you generically get by creating an electromagnetic field through a charge or through a current will have a rather small delta B compared to the expectation value of B, which means that we can write that the B field operator acting on the electromagnetic field gives you basically the expectation value of the electromagnetic field acting on that field vector again. So you almost have here an eigenvector, so it's almost not entangling. Almost not entangling, therefore the electron is almost unitarily evolving in an electromagnetic field, even if that electromagnetic field is very strong. Like when an electron is orbiting in a magnetic field. The point is that the magnetic field is supposed to be, for this to work, in a state in which the fluctuations of the electromagnetic field are small compared to the expectation values. Right, that is that's that. So just to summarize, what we found is that when you drive a harmonic oscillator externally, then you end up, it ends up in a coherent state. Coherent states are close relatives to squeeze states. It depends. It's a matter of perspective. It depends on with regards to which harmonic oscillator you consider them. They are always on the boundary of the uncertainty principle. They're saturating the uncertainty principle. Therefore, they are the states for which it is the easiest to have small quantum fluctuations relative to the expectation values, which makes them effectively classical. And effectively classical in this particular sense, for example. Namely, you have electrons moving, for example, in an electromagnetic field whose quantum fluctuations are small compared to the expectation values. Then we can see in this way that the interaction between the electron and the electromagnetic field is very little entangling. Therefore, the interaction is very little decohering. And that is why, in the first course in quantum mechanics, it is justified in the Schrödinger equation to just plug in a classical potential or a classical magnetic field. There is a lot of assumption behind it, but now I hope you see where that comes from. Okay, that's it for today. Any questions?